So I am Ali from Air University. I just completed my MS and I'm working towards my PhD. And this is the poster I designed for the conference. And first of all, I would like to congratulate all of you for the conference. Let me just start. I will not take a lot of time as there was a corona case in our institution reported yesterday, and it's a hectic routine from yesterday for that. So, okay. The topic, the title of my poster was Identifying Motion State Hemodynamic Changes in the Motor Cortex Using fNIRS to Control a Prosthetic Arm. I basically work with the prosthetic devices for last like 3 years. My bachelor's, from my bachelor's actually, I am working for transhumeral amputees to make a working prosthetic device for them. This is a lot of words here for the abstract of the poster. It actually states I actually implemented that on for transhumeral amputees and extracted the fNIRS intentions from the motor cortex, the hemodynamic responses. We were able to acquire like 80% accuracy in real time for like 10 motions. 8 motions were performed correctly using the LDA and the artificial neural network. I applied both the classifiers, both the linear and the non-linear, as the signals are inconsistent. So for the most of the training purposes and offline evaluation of the signals, it was artificial neural network. The experimental paradigm we designed was to set a initial rest of 30 seconds, and then there was a task. As I stated, I work on the prosthetic arm for transhumeral amputees. So we chose 3 degrees of freedoms for to acquire the signals for the motions. It actually includes elbow extension, elbow flexion, wrist extension, wrist flexion, and wrist supination and wrist pronation. All these tasks were acquired simultaneously and also sequentially. By simultaneously and sequentially, I mean that like all the 6 tasks, first they were like lined up. The subject knew what to perform. So the intentions were already marked that the first motion he will perform, the subject will perform, will be, for example, elbow extension. After that, the next 6 motions we recorded were not really intentional. It were really intentional. We had no cue for the subjects to perform any motion or something. We just wanted them to perform a motion, and it can be any motion, not even the defined 6 motion, just to uh, you know a barrier or a so we can have a broader idea of how the FNIRS intentions will come off, as there is no work is done yet on the FNIRS for non-invasive work actually with FNIRS for transhumeral amputees. Thanks to NIRS Technologies for providing us with their high functioning machine. It's actually the first machine in Pakistan that can record the brain signals. Due to limited resources here, we don't have much. We wrote a proposal and it took almost a year for this machine to actually we can acquire this machine right here. There were a lot of problems both financially and also the shipping problems and all that, but at the end we got the machine and it is helping us really well. We are not only driving just prosthetic devices with these, we are also working on the gait rehabilitation that happens with the legs, and we are also invited in the next week to a hospital to record the brain activities of anesthesia and dementia patients. As I told you, there is no such brain activity recording machine in Pakistan before this, so we really come into it really highlighted. So for my work, this is the framework. And the signals were acquired from the motor cortex, as you can see from the subject's head, and the neural activity was recorded. These yellow, blue, and red show how much the response, how strong the response was from yellow to red. The higher the concentration of oxygen changes, the more it went to red part. Then we acquired the neural activities, the hemodynamic responses, and there was a slide signal pre-processing that we have to do with fNIRS, filtering the signals and all that. Then we extracted the features for using the 2-second window, the mean feature and the peak feature. The minimum feature we extracted so that we can choose the optimal channels, because there are like 16 or maybe 32 or 16 optodes or electrodes placed on the head surface. We cannot, or you can also see that from the brain surface, that not all the electrodes are activated, not all the brain area is activated. So we extracted the minimum feature so that we can separate the activated and non-activated regions. Then there was signal classification using linear discriminant analysis and the neural networks, which helped a lot to generate a control command. Objective were obviously first was to acquire the signals, as there is no known data set. According to my knowledge, there is no data set present for transhumeral amputees from motor cortex, and obviously then we have to optimize the channel or brain region. Then enhancing the control command generation accuracy. I told you there is no such paper yet on this, using this modality for control of a transhumeral prosthetic arm. We used electromyography earlier for 4 motions, but as it is a transhumeral amputation, the muscle dies, and the electrical signals coming from the muscles, they die too. So it was not really helping the electromyographic intention. So we switched to fNIRS and acquired the machine, and then did our research. The signal processing, this is a signal processing block diagram. The motions were performed by the healthy and as well as the amputated subjects. I cannot show you the videos or the pictures of amputees because of the funding body. They don't want us to really publicize all the information right now because it is still under, we are still working on it for further, obviously for increasing the number of control commands, and also the consent they provide, the amputees provided. Yeah, they don't want their pictures to be shown publicly. So the motions were performed, the signals were acquired, and signals were pre-processed, like I told you, filtering. Then the instructions were separated, features were extracted, and they were labeled and saved as vectors. Then we split the data. As I told you that some motions were intentional and some were not intentional motions. We do not know which motions that could be. And that really helped us in the testing, for the testing environment, real-time testing, because we already trained the classifier for such uncertainties, and in real time it gave good results. Then we just classify out of the sample data and calculated the performance metrics, and it turned out that 85% we were getting offline accuracy ranging from 65 to 85%. Uh, and when we implemented it on hardware on real time, the amputees cannot wear the prosthetic arm yet, but we placed the prosthetic arm. It was a clinical experimental setting. The 8 commands were correctly classified, so it was a big plus point for 6 commands, because fNIRS accuracy dropped down with such number of commands. We have seen that in literature, not for transhumeral amputees motor cortex, obviously, but for other applications. As the number of control commands or classes increase, the fNIRS accuracy decrease. So this was a very promising and good result for us. So now we are trying to increase the number of control commands to 8 or 10 using the fNIRS with the EMG. So it will be kind of it is kind of a Actually, we have done it. It is kind of a hybrid system. Uh, Four or three commands control commands generated by EMG, and five or six will be are generated from the fNIRS. That paper I should not talk about. It's under review in the transactions. I don't know when they will respond to that, but we have also done that hybrid model. Moving on, the applications are not limited to just control of prosthetic devices. We can also use fNIRS for home automation. The NIRS technologies, they are working on new optodes. They call it the bundled optodes. It will cover less area because not every time all the brain regions are activated for specific activities. So it is really hectic to wear that cap for signal acquisition and to control. So let's see where that technology will lead, and we can also use it in hazardous environment like nuclear power plants, or like in corona also, where human contact is not advised. We can control the manipulators because we can implement a controller like ESP or Raspberry Pi into the hardware, and we can control it through Wi-Fi. The control commands can be translated, the signals can be translated to control commands via Wi-Fi, so the robotic manipulators can do the human work in such environments. So this is a plus point. These are the fNIRS signals. On the right side, you can see that the amputee subject filtered fNIRS signals are shown, and on the left side, there are healthy subject filters shown. These are so smooth looking signals, but actually, it's because the x-axis, it is the whole for 500 seconds. If we, I was trying to see if I can find that picture. I will show you later if I find it. You can see that for like a chosen window of 2 or 2.5 seconds, it is a very disturbed signal. So it is not that smooth like it is showing right now. These are the raw hemodynamic responses from the brain. You can see that like 3, 4 channels, like channel number 17, 15, 14, and a bit of channel 7, yeah, they are just activated. So we really need channel optimization here, and that is why we extracted the minimum feature to exclude all the other channels. It will help us in the real time control command generation. Obviously, there will be less computational time, less cost, computational cost. So a control command will be generated fast rather than implementing it on all 20 channels. We can select like 4, 5, 6 prominent channels to just translate that into control command. Here you can see the activated brain region, like the red one shown in the brain surface, and the head surface you can see the green region or the blue region. The dots in the red and yellow, these are the optodes. So you can see that there is no prominent activity. The red is only about on three maybe optodes. The red portion is. So that is why we have to select the optimal channels for the optimization, or else it won't work. So these are the accuracy results. 15 healthy subjects and 3 amputees. For now, the results are shown here. Others will be. You can see that I recently published a book chapter with Intech Open, book with the Intech Open publishers. It has all more information than this presentation. Obviously, it is just a glimpse of almost that paper. So you can find more results and discussions and things of your interest in the chapter. It is just published on 30th October. It is made public. So these are the classifier results. You can see that almost we are getting from the amputees, obviously. Yeah, this was an interesting fact that not only EMG perform bad when the residual muscle is not enough, or there is more time to amputation. Like this one, you can see the amputee number 2. he was amputated for like 42 months. So even his brain responses were not that strong as compared to the other amputees. One was amputated for a month, and the other was for 3 weeks. He was just amputated. So this was also a finding that the more the time to amputation, the brain hemodynamic responses also die. So nowadays we are working with the prefrontal cortex for like to generate control commands with the logical operations like arithmetic operations or word formation, and that is another story not related to this one. But yeah, motor cortex from the brain is not enough to control if there is time, a lot of time till amputation. The conclusion, yes, obviously, the 8 out of 10 motion was correctly predicted. It is one of a kind of a result because it is not done yet by anyone, especially for transhumeral amputees. fNIRS have been used for hand prosthesis problems or amputated problems, but not for the transhumeral amputation. So thanks to Nurse Technology for providing us with their high functioning device, we were able to do this, and I hope that we will achieve more in the future with these. So if there are any question and answers, I can switch to that. Thank you.